Neil Gershenfeld. I direct the Center for Bits and Atoms at MIT, and it's a interdisciplinary cross-campus program looking at the boundary of physical science and computer science. CBA grew from a group of people like me who never understood the division between hardware and software, or physical science and computer science. And so it was born with an NSF center proposal to assemble tools to make anything of any size on any length scale, and array around that a range of disciplines. And so the participants each have a discipline background: physics, chemistry, biology, many different disciplines that fits, but a piece that doesn't fit, looking at things like information and computation in physical systems. And so what's emerged from that broadly you can think of as, quite literally, how do you turn data into things and things into data? So in one direction, research on the future of fabrication, ways to digitize construction, and in the opposite, how to turn physical objects into data, all kinds of sensors and architectures for computing and things like that, problems where you can't separate digital and physical. My background's in physics, but I always at this boundary of physics and computing. I was a junior fellow at Harvard. I was almost going to go to IBM and take over Dick Garwin's lab. I had a lot of collaboration there. And through Marvin Minsky, I visited the Media Lab for fun and helped Todd Macover-Micacello for Yo-Yo Ma. And that led to create a physics group initially in the Media Lab. And that became eventually the Things That Think Consortium. And in that period, we developed early work on what helped become Internet of Things. Or my colleague Joe Jacobson, who was one of the founders of CBA, invented electronic ink. A lot of those projects of computing in non-traditional forms. And then in turn, CBA grew out of that when we started tackling things like molecular quantum computing or radio frequency control over biology, where the metaphor of digital and physical became much literal. And so there's a transitional period from things like our early work on intelligent infrastructure for buildings or Internet of Things or electronic paper displays to this much deeper integration of computation and physical properties. And so that led to many years of building the facility we now run that, from the scale of molecules to buildings, lets us make and measure things. And a lot of the tool building I'm describing. And now these maturing programs on how to turn data into things and things into data. And so from where we are now, in the research, there's maybe 20-year scale roadmap from here to the fully universal atomic assembler and the scalable bulk nano computer. Those sort of projects are beginning to mature into roadmaps, for the coming decades. And so one sort of thing we'll be doing is really executing on fulfilling that promise.